leave that one to the end. But when we get that under our belts, we're going to talk about two really cool animals, quahogs and sea urchins, that live for an incredibly long time. They've actually had some solid work done on them. And we'll review what's been learned about them. And we'll find out that basically I was not surprised, and I was hoping that there would be something new, but what really happens is the same problems with aging research that we're having in terrestrial environments actually are sort of coming up again in the marine environment. So aging research is kind of a crisis at the well, not crisis. It's very exciting because everything is being turned upside down, and I'll show you why before we're done. So first of all, in my blurb, I mentioned jellyfish and sea anemones. So I read this really cool news release about this jellyfish. And what this jellyfish apparently does is it pulls this trick where it goes back to being a kid and then grows up kind of up to like a 20-year-old human, and then goes back to being like a 7-year-old. And then grows back up again. And then it goes back. So in theory, it could live forever. Right? That's pretty good. But the problem is, do you really, first of all, as a human, do you want to do that? Because it's going to rewire your brain. You're probably going to be an entirely different person. You're going to have to shrink. And the mechanism there is so weird that it's actually not really going to shed that much light. And there's not a lot known. You can't really follow a jellyfish over. It's hard to do demography. If you don't know how long they live, how do you tag a jellyfish and see how many times it's gone through that cycle? It's difficult. The other one that I heard is sea anemones, and this comes from watching them in an aquarium. So if you watch a sea anemone in an aquarium, some people reported it was living on 60 to 80 years. This was actually one thing that got me into ants, because the world record for the lifespan for an ant was done in a little on someone's desk in one of those sandwich type ant nests. It was your little ant you have here. There's laziest nitrogen, little black ants. You see them like beans and then a lot that are on the sidewalk. And the queen from one of those lived 27 years. So that is what sort of one of the things that piqued my interest. But the same thing, the problem here is they're soft body. How do you estimate how old they are in the wild? If you actually go out and start looking at the sea. So you need that. They're almost not studied, it turns out. Then, of course, there was this big report where, unfortunately, this is the well, I guess, where they were doing Native Americans were doing their loud harvest, and they found this harpoon tip. It got nicked up by a chainsaw when they were butchering the well, but it dated that well being 130 to 160 years old. That is a very old animal. Now, it seems like that would be kind of cool, but again, how do you study something that old? But the real problem is it's big. And lifespan and size correlate. They have to, right? Because if you're going to be real old, if you're going to be big, you have to live long enough to get that big. So there's always some sort of a general sort of correlation going on. And this really complicates aging research because also with size, metabolic rate correlates with size. So the small animals tend to have a faster metabolic rate than big animals. Small animals also tend to be shorter lived than big animals, so you can get this, you get these correlations going, sort of can send you down the wrong path. So it gets confusing. So what really strikes me as interesting is to try to find, are there any small animals that live a very long time? And this is where, when I was looking around the mortality rate changes with time. So you have a high infant mortality rate, right? So babies tend to have a higher probability of dying, and then when they reach about 7 or 8, then it plateaus, and then your mortality rate goes up, and it stays about steady to the 20s and 30s, and then this mysterious thing happens. It starts ticking up. The straight line on this sort of graph means that your mortality rate is essentially going up like interest. So it's like in humans, every 8.5 years, your mortality rate doubles. So the way to think about this is, what's your probability of dying today? What's your probability of dying tomorrow? And what's your probability of dying the next day? All right. So for a baby, once you're born, it's fairly high. Once you make it, through your early childhood, it goes down. So your probability is better. You're less likely to die. What's cool is when you get in here, 20 to 30-year-olds are, by definition, some definitions, immortal. Because, which is lovely, tell them. So their probability of dying today is the same as it's going to be tomorrow, the same as it's going to be the next day. They are basically not aging. Some people have labeled this healthy aging because you're ticking up chronological years. But your risk of death, the risk of mortality, isn't going up. All right? So they really are immortal. Then, somewhere in here, something bad happens. Okay? So once you get over 30, 35, then it ticks into this strange thing where it starts going up constantly. Boom, 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 boom. So you start going up. We aren't going to talk about the leveling off, mostly because the theoreticians haven't figured that part out. Oops. I'm terrible when my hands on the stick. So aging then is an increase in the probability of dying over time. So you have to think about it not as a maximum lifespan or even average lifespan, but it's how your probability increases as you age, or not increase. So what's special? What do you think is the special going on at that point? Anybody have any idea? Yeah?
Probably connected to something that you've already had your progeny, if you're going to have any.
Right. So you're thinking that there's something to do with offspring, with reproduction, right?
Once you've had a reproductive period, then you start to age.
Well, that would be fine, except why not just stay reproductive out here? You're getting close. This is where we have to start talking about evolution. Basically, what happens is, I'm not arguing that the force of natural selection falls off with time. When you're really, really close, that's where you've had your progeny. But then you have to ask that question, why don't you just keep having progeny? It seems like that would be the best strategy, right? So, okay. So what we have to do, though, we have to understand what's going on out here. Why is it not beneficial to just keep cranking out progeny? I mean, there's a real sort of history here, right? fluffy feet, really silly looking things. But the point is there's a lot of variation out there, and it can be inherited. All right, so there's this heritable variations floating around out there in the world. I think that's one premise most people don't have a problem with. You can see it when you look at it when you're breeding dogs. You see it when you look at your kids. There's just evidence of that part everywhere. The second thing he noticed was that, but this was a bit more subtle, was there's an intense competition all the time for survival. And this competition is really, really severe. So I went out and picked a dandelion head, which is there. How many seeds do you think are there? 1,000, 300, 200, getting warmer. 218. This is the kind of stuff you have to put up with if you marry a biologist. I'll go out, get a dandelion. Believe me, I've had far worse in our kitchen. You see it in our freezer sometimes. I've been out collecting bugs. So I picked them all out and I counted them. So 218 seeds. So now, if you imagine that the population, the world level of dandelions is basically going to be the same over a period of time. You aren't going to, if it wasn't, maybe dip deep in dandelions, right? So dandelions obviously have more heads than just one throughout their lifetime. So if you imagine there's thousands of dandelions, how many of all those seeds, how many on average are going to make it to replace the next one? I heard it already. One. So if you have a steady population, you have all those offspring, only one is going to make it. All right? So it's really, really intense competition. So anything that gives you an edge is going to help. The way to think about this is if you consider you're applying for a job against 10,000 other people. Okay, if you're competing against a job and there's only 5 resumes that you have to go through. Let's say you're the one who's sitting there sorting through the resumes. You have a stack of 5 resumes. You know, you see a misspelling. Okay, you may keep it. But if you have 10,000 resumes to go through, anything misspelled, any reason at all, you're going to be chucking it, right? So this force of selection gets stronger and stronger as you, as the population size, the number of individuals increases. What that means is that even very, very slight things can be selected. Okay, so anything gives an animal an edge, or gives an offspring an edge, is going to have a big effect. So, very, very large population selection can work on really minor traits. So, any other help? Now, this is the sticky point. This is the one that is critical and probably the hardest to get. And that is this idea of geological time. Lamarck saw that was important. Darwin realized how important it was. And it turns out it's one of the hardest things to sort of get your head around. So what we're going to do is we're going to try a different plot. So usually in textbooks they use this clock face analogy where you say, okay, imagine the world starts at midnight and it goes around, you have prokaryotes showing up at about 4 in the morning, and oxygen at about 6, and then multicellular eukaryotes somewhere in here, and then animals start at about 11. That's all well and fine. If you want to learn about the relative timing of things. What you really need to get evolution So from this line, that'll be today. And since we're using a clock, we'll call the clock Big Ben. So we'll go up to Big Ben. So this is just a Google map from Knox, where we're sitting here. And I did a route, just hit the Google directions from Big Ben to Knox. So Big Ben's up here in London. So this is our timeline. So we're going to play a game. We're going to see how many of you can figure out when life originated. Okay? So let's have everybody put your hands up. And then I want you to put your hands down when you think I get to the point where life arose. Okay? So hands up. Okay, so when we get about half people, we'll decide it's about there. So we're starting off Big Ben, we're driving out here. How many? Okay, roughly up 25. Coming down here, 25. That's still coming down. Okay. Morning Bridge, I think. Do you think it was somewhere in here? No, a little even further west. So you think it started. Okay, somewhere in. That was about half. I think we're somewhere